The date was September 16, 1943. The location was Bougainville in the Solomon Islands. First Lieutenant Kenneth Walsh sat in his cockpit after another mission. His hands moved across his personal logbook. He was recording observations that would mark a turning point in Pacific air warfare. Everything was about to change with these new aircraft. The speed advantage was undeniable. The firepower exceeded anything they had seen before. These capabilities gave American forces advantages that the Zero simply could not counter. But accuracy remained the critical issue. Deflection shooting still challenged even the most experienced pilots. Walsh peered through the scratched and weathered plexiglass of his F4U Corsair canopy. He had just returned from another bomber escort mission. The familiar problems had shown themselves again during the flight. Striking a target that was maneuvering while both aircraft executed violent turns demanded mathematical precision. Human minds struggled to perform these calculations in fractions of seconds. The pressure was enormous. The margin for error was non-existent. Walsh and thousands of other Marine and Navy pilots had no way of knowing what was coming. British engineers had already solved this exact problem. A revolutionary device was being perfected thousands of miles away. Spinning gyroscopes and precision mirrors would soon transform aerial gunnery forever. The art that required years of experience would become a science. New pilots could master it in weeks. The Mark 18 gyroscopic gun sight was already in production. It would reach the Pacific theater within 12 months. The mathematics of air combat would never be the same. The Vought F4U Corsair had entered combat in February 1943. It brought unprecedented speed and firepower to Marine aviation units. The massive Pratt & Whitney R2800 double Wasp engine dominated the aircraft's nose. This powerhouse produced over 2,000 horsepower. The Corsair could exceed 400 miles per hour in level flight. It became the first American single-engine fighter to break that barrier. 6 Browning M2 machine guns lined the wings. Each weapon fired .50 caliber ammunition. The rate of fire approached 800 rounds per minute. The firepower was devastating when bullets found their targets. Making those bullets connect remained the challenge. Deflection shooting represented the most difficult aspect of aerial combat. The art of hitting a moving target from a moving platform tested every pilot. A Corsair traveling at 400 miles per hour faced a Zero executing evasive maneuvers at 300 miles per hour. The pilot could not aim at where the enemy was. He had to aim at where the enemy would be when the bullets arrived. Those .50 caliber bullets left the guns at approximately 20 to 700 feet per second. Even at that velocity, time was required to reach the target. At 500 yards distance, that flight time approached half a second. A Zero in a standard rate turn would cover nearly 200 feet in that interval. The pilot had to lead the target by exactly that amount. The lead angle changed continuously as ranges and angles shifted. G-forces pressed against the pilot during maneuvering. Vision narrowed under the physical stress. Complex mathematics became impossible to perform. The Mark 8 reflector sight was standard equipment on Corsairs through 1943 and early 1944. It offered no assistance with deflection calculations. The device projected a simple illuminated reticle onto a glass plate. Nothing more than a fixed reference point showed where the guns were aimed. The pilot estimated lead angles entirely through experience and intuition. Some pilots developed a feel for deflection shooting after months of practice. Their hands moved instinctively to the correct positions. Their eyes calculated angles without conscious thought. Many pilots never developed that intuitive sense. They consistently fired behind fleeing targets. Precious ammunition was wasted, shot after shot. That ammunition had traveled 6,000 miles across the Pacific to reach them. Lieutenant Kenneth Walsh flew with VMF 124. He had mastered deflection shooting through relentless repetition and natural ability. May 13, 1943, marked a significant milestone in his career. He became the first Corsair ace by shooting down 3 Japanese fighters in one day. His total confirmed victories reached 6 aircraft. Walsh had learned to anticipate target movements before they happened. He could sense the proper lead angle through instinct. His finger found the trigger at the precise moment when geometry and intuition aligned perfectly. His success came from hundreds of hours of practice flights. An innate understanding of three-dimensional motion separated him from average pilots. Most pilots lacked Walsh's natural gifts. The typical Marine pilot arrived in the combat zone with perhaps 200 hours of total flight time. Maybe 20 hours involved actual gunnery practice against towed targets. Those targets flew straight and level courses. They bore no resemblance to maneuvering Zeros flown by experienced Japanese pilots. Average pilots struggled to achieve any hits against real combat targets. Combat reports from 1943 revealed a disturbing pattern. Many pilots expended all their ammunition without scoring a single victory. Their bullets passed harmlessly behind enemy aircraft. Mental calculations were fractions of seconds too slow. The enemy was gone before the bullets arrived. The British had recognized this fundamental problem early in the war. Ferranti began producing the Mark II Gyroscopic in 1941. This revolutionary device used spinning gyroscopes to calculate deflection angles automatically. The underlying principle was elegantly simple in concept. Gyroscopes naturally resist changes in their orientation. When an aircraft banks or turns, the gyroscopes inside the sight remain pointed in their original direction. The aircraft rotates around them while they maintain their spatial reference. Precision gears and mirrors measured this resistance to movement. The sight calculated the aircraft's rate of turn from these measurements. That rate of turn corresponded directly to the lead angle required to hit a target. The sight automatically adjusted the aiming reticle to compensate for this movement. It moved the reticle ahead of the target by precisely the correct amount. Royal Air Force pilots using the Mark II Gyroscopic reported dramatic improvements in their accuracy rates. Spitfire pilots, who had struggled with deflection shooting, suddenly found success. They were hitting targets on their first burst of fire. The sight eliminated the need for complex mental calculations during combat. Pilots could focus on tactics and positioning rather than geometric calculations. Their minds were free to process the larger tactical picture. The United States recognized the technology's potential immediately. Contracts were awarded to Sperry Gyroscope Company to produce American versions. The U.S. Army Air Forces designated their version the K-14. The Navy and Marine Corps called theirs the Mark 18. Both were essentially identical to the British Mark II. 2. Design. Minor modifications accommodated American manufacturing techniques and cockpit integration requirements. Sperry's facility in Lake Success, New York, employed over 20,000 workers at peak production levels. They turned out gyroscopic gun sights alongside bomb sights and fire control systems. Navigational equipment rolled off the same production lines. The industrial capacity was staggering in its scope and efficiency. The Mark 18 was substantially larger than the simple reflector sight it would replace. The Mark 8 reflector sight was a compact unit weighing perhaps 5 pounds. The gyroscopic sight system weighed 12 pounds and required significant cockpit modifications. Sperry engineers explained that the additional bulk was absolutely necessary for proper operation. Inside the protective housing were 2 independent gyroscopes measuring pitch and yaw movements. These gyroscopes spun continuously once electrical power was applied. They contained the secret to solving deflection shooting problems. This represented the single most difficult aspect of aerial gunnery. Fighter pilots had struggled with these challenges since the First World War. The Mark 18's design incorporated lessons learned from extensive British combat experience. The sight featured two independent reticles visible to the pilot during operation. On the left side, a fixed cross indicated where the guns were actually pointed. This provided a constant reference for the aircraft's bore axis. On the right side, a gyro-stabilized reticle showed the computed aiming point. This reticle consisted of a center circle surrounded by 6 diamond-shaped pips. As the pilot maneuvered to track an enemy target, the gyroscopic reticle automatically positioned itself ahead of the aircraft. The lead angle was calculated with mathematical precision. The pilot's operating procedure was dramatically simplified compared to reflector sight operation. First, the pilot set the target's wingspan using a control knob on the sight itself. He selected from known values for various Japanese aircraft types. The A6M0, the most common opponent in the Pacific, had a wingspan of 36 feet for standard variants. With wingspan selected, the pilot adjusted a twist grip integrated into the throttle lever. This action expanded or contracted the diamond-shaped ranging reticle. The pilot matched it to the apparent wingspan of the target as seen through the sight. This procedure mechanically set the range to the target. The sight's ballistic computer now knew how far away the enemy aircraft was. It could therefore calculate exactly how much bullet drop to compensate for at that distance. With range and wingspan properly set, the gyroscopes assumed control of the aiming process. As the pilot maneuvered to track the target, the moving reticle automatically positioned itself ahead of the enemy aircraft. The lead angle was exactly correct for the current rate of turn being flown. The pilot simply placed that computed reticle on the target and pressed the trigger. The bullets would arrive precisely where the sight predicted they would. This accuracy was maintained regardless of how complex the maneuvering became. Production of the K-14 and Mark 18 began in earnest during spring 1944. The U.S. Army Air Forces received priority allocation for European theater operations. P-51 Mustangs and P-47 Thunderbolts began receiving K-14 installations in August 1944. The Navy and Marine Corps followed closely behind in the production queue. F4U Corsairs and F-6F Hellcats were scheduled for Mark 18 retrofits through fall and winter 1944. The first Corsair squadrons to receive the Mark 18 were those preparing for carrier operations. VMF-124 and VMF-213 were designated as the first Marine fighter squadrons assigned to fleet carriers. They received their gyroscopic sights during training at Naval Air Station Santa Barbara in late 1944. These squadrons would join USS Essex in December 1944. This deployment would bring the Corsair into carrier-based combat for the first time in the war. Lieutenant Robert McClung flew with the reformed VMF-214. He received his Mark 18 equipped Corsair in early 1945. McClung had scored several confirmed victories during 1944 using the standard reflector sight. His experience gave him an immediate appreciation for the gyroscopic sight's revolutionary potential. In a letter to his family, later preserved in Marine Corps historical archives, McClung wrote about the transformation. The Mark 18 represented the difference between skilled guesswork and mechanical certainty. The device compressed years of hard-won experience into a few hours of training. New pilots could achieve what had previously required months of combat experience to develop. Japanese naval aviation intelligence first became aware of American gyroscopic gunsight technology in late 1944. Analysis of recovered Corsair wreckage provided initial clues. Interrogation of captured American documents confirmed their worst fears. What they discovered in those technical specifications alarmed Japanese tacticians profoundly. The Americans had developed a fire control system that largely eliminated human error in deflection shooting. The mathematical precision was beyond anything Japanese technology could match. Japanese tacticians understood immediately that this technological advantage could not be countered through improved training alone. Modified tactics would not be sufficient either. The mathematical precision of gyroscopes spinning thousands of times per minute could not be matched by human reflexes. Experience levels became irrelevant against such mechanical precision. Japanese fighters had survived thus far by exploiting their superior maneuverability. They forced American pilots into difficult deflection shots, where human calculation errors provided margins of safety. Against Mark 18-equipped Corsairs, those safety margins vanished completely. Any American pilot who could track a Japanese fighter long enough to set range would score hits. The complexity of the maneuvering involved became irrelevant to the outcome. Tactical modifications were ordered across all Japanese naval aviation units immediately. Japanese fighters received instructions to avoid prolonged turning engagements with Corsairs at all costs. The new doctrine emphasized hit-and-run attacks exclusively. Fighters would dive from altitude to make a single firing pass. They would then extend away at maximum speed without engaging in turning combat. This tactical shift acknowledged an uncomfortable reality for Japanese aviation. Pilots could no longer rely on maneuverability alone to survive against technologically superior gun sights. The rules of aerial combat had fundamentally changed. Traditional advantages had been neutralized by American industrial and technological superiority. December 1944 brought a significant milestone in Corsair operational history. VMF 124, commanded by Major William Guise, became the first Marine fighter squadron to operate from a fleet carrier. They joined USS Essex at the forward anchorage at Ulithi Atoll. VMF 213 joined the ship simultaneously. This brought 48 F4U Corsairs to carrier operations for the first time. Both squadrons were equipped with Mark 18 gyroscopic gun sights. They represented the cutting edge of American aviation technology in both aircraft and fire control systems. The Essex Air Group sortied in January 1945 for strikes against Formosa and the Philippines. Marine Corsair pilots flew combat air patrol missions. They provided bomber escort services and conducted independent strike missions. The F4U was finally entering the carrier-based role for which it had originally been designed. The Mark 18 proved invaluable during these initial carrier operations. Pilots engaging Japanese interceptors reported significantly improved hit rates compared to their previous experiences. Combat action reports from January and February 1945 documented numerous instances of remarkable accuracy. Pilots achieved kills with their initial burst of fire. This level of first-pass success had been uncommon with earlier sighting systems. The difference was most apparent during bomber escort missions. Corsairs maintained formation positions that often prevented ideal attack geometries. The Mark 18's ability to calculate accurate deflection from any angle transformed these constrained engagements. What had been disadvantageous positions became viable attack opportunities. Pilots no longer needed to maneuver into perfect 6 o'clock tail positions behind enemy aircraft. They could engage effectively from deflection angles that would have been impractical with reflector sights. High-side attacks became viable. Beam attacks produced reliable hits. Head-on passes resulted in consistent target destruction. The tactical flexibility was revolutionary in its implications. February 1945 brought the invasion of Iwo Jima. Marine Corsairs provided continuous air cover for the massive assault force. Multiple Marine squadrons flew from escort carriers positioned off the island. They maintained combat air patrols over the invasion fleet around the clock. Ground support operations continued throughout the bitter fighting on the island. The Mark 18 equipped aircraft demonstrated their effectiveness during defensive missions against Japanese air attacks. Pilots intercepting incoming raids consistently achieved kills at ranges and angles that would have been difficult with older sighting systems. The gyroscopic sight's automatic deflection calculation allowed pilots to engage multiple targets in rapid succession. A pilot equipped with a reflector sight might have expended all his ammunition on a single difficult target. Mark 18 equipped pilots could achieve hits on 2 or 3 targets during the same engagement. Ammunition was conserved while combat effectiveness was multiplied. Squadron commanders noted this transformation in their operational reports. Less experienced pilots were achieving combat effectiveness levels comparable to veteran airmen. This improvement was attributed primarily to the enhanced fire control provided by the gyroscopic sight. Training time was reduced while combat results improved dramatically. The technology was proving its worth under the most demanding combat conditions. March 1945 saw the continuation of carrier operations against the Japanese home islands. VMF 214 aboard USS Franklin participated in strikes against Japanese airfields and military installations. On March 19, 1945, Franklin was struck by a Japanese bomber while operating off Kyushu. The resulting explosions and fires killed over 700 men aboard the carrier. 32 members of VMF 214 were among the casualties. The squadron suffered devastating losses in personnel and equipment, but the survivors continued their mission after Franklin limped to safety. The disaster highlighted both the extreme dangers of carrier aviation and the extraordinary courage of the pilots who flew these missions. Despite the tragic losses, Marine Corps air squadrons continued their assigned missions. They provided essential air cover and strike capability for the Pacific Fleet. The war effort could not pause to mourn the dead. New pilots and aircraft replaced those that had been lost. April 1945 brought Operation Iceberg, the invasion of Okinawa. This campaign would witness the most intensive kamikaze attacks of the entire war. Japanese forces threw thousands of aircraft against the American fleet in desperate attempts to halt the invasion. Marine Corsairs equipped with Mark 18 sights played a crucial role in defending against these suicide attacks. The gyroscopic sight proved particularly effective against kamikaze aircraft. These planes flew predictable attack profiles that made range estimation and deflection calculations straightforward for the automated systems. Pilots could acquire incoming kamikaze aircraft visually. They set range using the sight's ranging reticle with practiced efficiency. First burst hits occurred with regularity that would have been impossible with reflector sights. Combat air patrol missions during April through June 1945 resulted in hundreds of Japanese aircraft destroyed over Okinawa. Precise statistics specifically attributing kills to Mark 18 equipped aircraft versus those with reflector sights are not available in declassified records. However, operational reports consistently noted improved combat effectiveness among squadrons that had received the gyroscopic sights. The psychological impact on Japanese pilots who survived encounters with Mark 18 equipped Corsairs extended beyond simple tactical disadvantage. The experience of being hit, regardless of evasive maneuvering, created a profound sense of helplessness. Watching tracer rounds curve through the air with unnatural accuracy was deeply demoralizing. Traditional training had not prepared them for this level of technological superiority. Post-war interviews with surviving Japanese aviators revealed telling insights. Many identified advanced American fire control systems as among the most demoralizing technologies they faced during the war. The certainty of being hit once an American pilot achieved a tracking solution eliminated hope. That hope had sustained Japanese fighter pilots through increasingly desperate circumstances throughout the conflict. Maneuverability could no longer save them from destruction. Years of experience provided no meaningful advantage against mechanical precision. The only escape was to avoid engagement entirely. This became a tactical impossibility when defending against attacking bombers or protecting their own surface forces. The Mark 18's technical operation represented a remarkable achievement in mechanical computing technology. The system operated without any electronics whatsoever. Purely mechanical linkages, precision gears, and carefully aligned mirrors performed calculations that would challenge a trained mathematician. The gyroscopes spun continuously once the sight was powered by the aircraft's electrical system. They maintained their orientation in space through the physical principle of conservation of angular momentum. As the aircraft maneuvered through the sky, the gyroscope housing rotated relative to the stable gyroscope rotors inside. Precision gears measured this relative motion with extraordinary accuracy. The measurements were translated into mirror movements that repositioned the aiming reticle accordingly. The entire system operated with tolerances measured in thousandths of an inch. Manufacturing required the most advanced machining techniques available in 1944. American industrial capability was pushed to its absolute limits to produce these precision instruments in quantity. Sperry's production facilities represented the pinnacle of American precision manufacturing during the war years. Each Mark 18 required dozens of individual components machined to exacting specifications. The gyroscopes themselves were masterpieces of miniaturization and engineering precision. Spinning bearings had to operate smoothly under sustained high-G maneuvering without binding or mechanical failure. Quality control procedures tested each site extensively before delivery to operational units. Test stands simulated aircraft maneuvering across a full range of flight conditions. Engineers verified that each site correctly computed deflection angles across various turn rates and target ranges. Sites that failed these rigorous tests were returned to the factory for adjustment or complete rebuilding. The manufacturing challenge extended beyond simply producing the sites to acceptable quality standards. They had to be produced in sufficient quantities to equip thousands of aircraft across multiple theaters of operation. Sperry ramped up production capabilities throughout 1944. Workers were trained in the specialized skills required for precision optical and mechanical assembly. The Mark 18 benefited from American mass production techniques while maintaining the quality standards necessary for a precision scientific instrument. Parts were designed for complete interchangeability. This allowed sites to be assembled from components manufactured at different facilities across the country. Modularity also simplified maintenance and repair procedures in forward combat areas. When a site failed during combat operations, technicians could replace individual components rather than the entire unit. Sperry maintained parts stockpiles at maintenance facilities throughout the Pacific Theater. This logistics network ensured minimal downtime for aircraft requiring site replacement or repair. The integration of the Mark 18 into Corsair cockpits required careful attention to ergonomic factors. The site had to be positioned where pilots could easily view it while maintaining full situational awareness. The throttle-mounted range adjustment had to be readily accessible. Pilots could not be required to remove their hands from primary flight controls during combat maneuvering. Engineers worked closely with experienced combat pilots throughout the development process. They incorporated detailed feedback about what installation features worked effectively. They also learned what created difficulties during high-stress combat maneuvering. The final cockpit integration reflected months of testing and refinement based on real-world operational requirements. The Mark 18 became a system that pilots could use without thinking. No mental gymnastics required. No split attention between flying and figuring out the sight. Training programs emerged to teach effective Mark 18 operation. The emphasis fell on understanding visual cues. Pilots needed to know what the sight was telling them. They learned to spot the moment when gyroscopes settled after wild aerial maneuvers. Trust the computed reticle when it stabilized. Set range quickly using that distinctive diamond pattern. Ground instruction covered gyroscopic principles without drowning pilots in mathematics. The goal was battlefield competence, not engineering mastery. Pilots needed operational skills, not design theory. Flight training meant real intercepts against actual target aircraft. This gave pilots hands-on experience with sight behavior during tracking. Instructors hammered home one critical point. Smooth tracking was everything. Jerky maneuvers confused the gyroscopes. Accuracy suffered when pilots thrashed around the sky. The Mark 18 performed best during steady pursuit phases. Consistent turn rates let the gyroscopes work properly. The sight measured angular velocities accurately when inputs remained predictable. Training also revealed the system's weak spots. Gyroscopes needed time to settle after violent maneuvers. Several seconds of stability before full accuracy returned. A pilot pulling a sudden reversal would see the reticle lag momentarily. The sight took time to recompute deflection after dramatic course changes. Experienced pilots learned to work around these delays. They timed attacks for moments when the sight had achieved stable operation. These minor limitations didn't diminish the Mark 18's revolutionary impact. Despite brief lag periods after extreme maneuvers, the system represented a massive leap forward. Fire control technology had evolved beyond anything previously imagined. Pilots who had struggled with deflection shooting suddenly found success. Hit rates that seemed impossible became routine. The sight didn't make aerial combat simple, but it removed the hardest variable from the equation. Combat remained deadly and demanding. Tactical judgment still mattered. Situational awareness could mean the difference between life and death. Skilled flying remained absolutely essential. But the actual moment of shooting had changed fundamentally. When trigger met target, the outcome became more predictable, more reliable, more lethal. Measuring the Mark 18's specific impact on Corsair operations proves challenging. Official statistics show F4U Corsairs achieved an 11-to-1 kill ratio during World War II. They scored 2,140 air combat victories against 189 losses to enemy aircraft. These numbers came from 64,051 operational sorties across the Pacific Theater. The figures combine results from aircraft with reflector sights and gyroscopic sights. Separating the Mark 18's contribution from other factors requires detailed combat reports. Many of these documents remain classified or lost. The specific numbers may be unclear, but pilot testimony is consistent. Every pilot who flew with both sight types reported the same thing. The Mark 18 made deflection shooting more reliable. Natural ability mattered less when the sight did the calculations. Squadron records provide hints of the improvement. Pilot memoirs describe significant advantages in combat effectiveness. Operational summaries indicate the gyroscopic sight provided real tactical benefits. The Mark 18 program showcased American industrial might at its peak. The device combined cutting-edge gyroscopic technology with precision optics. Mechanical computing elements worked together in harmony. Everything was packaged to survive the brutal world of combat aviation. Manufacturing occurred in quantities sufficient for thousands of aircraft. Global supply chains delivered the sights worldwide. Forward area technicians maintained them under primitive conditions. The program succeeded through systematic execution rather than single innovations. British scientists had identified the underlying principle. American engineers adapted the design for mass production capabilities. American industry manufactured the units in massive volumes. American logistics delivered them exactly where needed. The Mark 18 embodied the systematic approach that characterized wartime production. Every element of the system functioned effectively together. Japanese perspectives on the Mark 18 evolved in post-war decades. Former aviators published memoirs analyzing their combat experiences. They participated in historical studies examining the Pacific Air War. The universal conclusion was sobering. American fire control technology had rendered Japanese tactics increasingly ineffective. By late 1944 and early 1945, maneuverable fighters couldn't compete. Well-trained Japanese aviators found themselves outmatched by automated deflection calculation. The most skilled pilot couldn't outfly mathematics. Post-war Japanese aviation development reflected these harsh lessons learned. The Japan Self-Defense Force, established in the 1950s, emphasized advanced avionics. Weapon systems took priority over aircraft maneuverability alone. Surviving pilots who had faced Mark 18-equipped Corsairs understood the future. Aerial warfare would be decided by technology, not individual skill alone. The Corsair itself continued flying long after World War II ended. Marine squadrons operated F4U variants during the Korean War. From 1950 to 1953, they provided close air support. Interdiction missions tested the aircraft in different conditions. Many retained their Mark 18 gyroscopic sights throughout operational service. Technology that seemed revolutionary in 1944 became standard equipment by 1950. What appeared impossible in 1940 was routine by 1950. The same capabilities were obsolete by 1960. The transformation of aerial gunnery accelerated dramatically. Art became science through technological advancement. This evolution reached its logical conclusion with guided missiles. Air-to-air missiles eliminated pilot aiming requirements entirely. First deployed operationally in the 1950s, missiles removed even the need for maneuvering. Pilots no longer had to point their aircraft at targets. The progression occurred in less than 15 years. Reflector sights, to gyroscopic sights, to radar-guided missiles. Military aviation history had never witnessed such rapid technological change. American pilots flying over Vietnam in the 1960s used sophisticated descendants. Fire control computers integrated the Mark 18's gyroscopic principles into far more advanced systems. These systems combined radar ranging with automatic lead computation. Ballistic calculations merged with target identification capabilities. Unified packages bore little resemblance to the 1944 mechanical computer. Yet the fundamental principle remained identical to the Mark 18's innovation. Measure platform motion using gyroscopes. Calculate required lead angles automatically. Present information to pilots in usable form. The statistical record provides context for understanding the Mark 18's role. Marine and Navy Corsair squadrons flew tens of thousands of sorties. From 1943 through 1945, they battled Japanese forces across the Pacific. The 11-to-1 kill ratio established the Corsair as one of history's most successful fighters. This success resulted from multiple factors working together. The Corsair's speed advantage over Japanese fighters was crucial. Pilots could control engagement geometry at will. They chose when to fight and when to disengage. Rugged construction meant the aircraft could absorb battle damage. Lighter Japanese aircraft would have been destroyed by the same hits. Heavy armament delivered overwhelming firepower when bullets found their targets. The Mark 18 gyroscopic sight amplified these existing advantages. It made delivering the Corsair's firepower more accurate and reliable. The sight didn't create the Corsair's superiority. It enhanced what was already a formidable weapon system. Pilot quality remained absolutely crucial despite technological assistance. The Mark 18 helped pilots shoot accurately. It didn't teach tactics, situational awareness, or combat judgment. These skills still required extensive experience and training. Natural ability and learned expertise remained essential elements. What the sight accomplished was compressing the learning curve. Deflection shooting had previously required extensive practice to master. The Mark 18 made this skill more accessible to average pilots. The broader historical context reveals the sight as one component. American technological superiority in the Pacific encompassed many systems working together. Radar systems provided early warning and intercept control capabilities. Radio communications enabled coordinated operations across vast distances. Proximity-fused anti-aircraft shells created defensive envelopes around naval vessels. Each technology individually provided significant advantages. Together, they created synergistic effects that Japanese forces couldn't match. The Mark 18 fit perfectly into this larger pattern. It wasn't a wonder weapon that single-handedly won the air war. It was a practical improvement that made effective aircraft more effective. The contribution was incremental rather than revolutionary in nature, but incremental improvements multiplied across thousands of aircraft mattered greatly. Tens of thousands of combat engagements benefited from improved accuracy. The cumulative effects proved significant, even if individual improvements seemed modest. The Mark 18's legacy extended far beyond direct combat applications. The development process required unprecedented collaboration between different groups. Scientists provided theoretical foundations. Engineers solved practical manufacturing challenges. Combat pilots gave feedback that drove iterative improvements. This collaborative approach became a model for future weapons development programs. The procurement process also established important precedents for future programs. Rather than developing entirely new technology from scratch, America recognized British innovation. The decision to adapt foreign technology when it offered advantages demonstrated pragmatism. This willingness to adopt the best solutions regardless of origin served American military aviation well. The approach continued throughout the Cold War and beyond. Manufacturing techniques developed for Mark 18 production had lasting impact. The program pioneered modular assembly processes. Different facilities could produce interchangeable subcomponents efficiently. This enabled the massive production volumes that gave American forces their technological edge. Similar techniques were later applied to radar systems and aircraft engines. Eventually, electronics manufacturing adopted the same approaches. This created an industrial base capable of producing complex precision equipment. Production scales became impossible for other nations to match. The pilots who flew with Mark 18 sights formed a unique generation. They transitioned from instinctive gunnery to technology-assisted combat. Many continued military careers flying jets in Korea. Staff positions allowed them to shape tactical doctrine around advanced fire control capabilities. Lieutenant Kenneth Walsh had become the first Corsair ace in 1943. He achieved this using only a reflector sight and natural ability. Walsh ended the war with 21 confirmed victories. He received the Medal of Honor for actions on August 15, 1943. That day, he attacked a superior force of Japanese aircraft despite damage to his own Corsair. Walsh survived the war and remained in the Marine Corps. He continued serving until his retirement, eventually reaching lieutenant colonel rank. His career spanned the transition from instinctive aerial combat to technology-assisted engagement. Aircraft evolved from machine gun armament to guided missile capabilities. Walsh's experience represented the broader transformation of aerial warfare. The mid-20th century witnessed fundamental changes in how air combat was conducted. Lieutenant Robert McClurg flew with the reformed VMF-214 in 1945. He survived the war with 7 confirmed victories. McClurg remained in the Marine Corps until 1965, retiring as a colonel. During retirement, McClurg wrote about the technological transformation he had witnessed firsthand. He emphasized that while the Mark 18 made deflection shooting more reliable, aerial combat never became safe or easy. The sight eliminated one variable in the complex combat equation. Countless others remained just as dangerous and unpredictable. Altitude management still required skill and judgment. Energy state awareness could mean the difference between success and failure. Situational awareness remained absolutely critical for survival. Tactical positioning determined engagement outcomes before shooting even began. A pilot with a perfect gun sight could still be outmaneuvered. Superior climbing ability could overcome technological advantages. Getting caught unaware by an unseen enemy remained deadly. The technology improved effectiveness within engagements. It didn't guarantee survival or eliminate other combat challenges. The Mark 18 story concludes without dramatic endings. Gradual evolution into more sophisticated systems marked its transition to obsolescence. Jets replaced propeller-driven fighters in the 1950s. New fire control systems replaced gyroscopic gun sights naturally. The Mark 18 didn't suddenly fail or become worthless overnight. It simply became outdated as requirements changed. Faster aircraft demanded more sophisticated solutions. Longer engagement ranges exceeded the sight's capabilities. Some Mark 18 sights remained in service aboard Corsairs flying close air support missions in Korea. Others were placed in storage as aircraft were retired. Many were scrapped when no longer needed. A few were preserved in museums where they remain today. These serve as tangible links to an era when mechanical computing represented cutting-edge technology. The Mark 18's legacy lives on not in physical devices. Museum pieces tell only part of the story. The real legacy exists in principles demonstrated and technological lineage initiated. Every modern fire control system, regardless of sophistication, traces intellectual heritage back to devices like the Mark 18. These first solved fundamental problems of automated aiming under combat conditions. The engineers who worked on the Mark 18 contributed knowledge extending far beyond their specific achievements. They demonstrated that complex calculations could be performed mechanically. Sufficient reliability for combat use was achievable through careful design. They proved that human-machine interfaces could be designed for operation under extreme stress. Sophisticated technology could be manufactured at scale and maintained under field conditions. These lessons informed decades of subsequent development work. The pilots who flew with Mark 18 sights contributed their own lasting legacy. They tested the technology under actual combat conditions. Feedback from operational use refined the design and operating procedures. Tactics were developed that exploited the sight's unique capabilities. Most importantly, they proved that humans could effectively partner with automated systems. Neither complete dependence on technology nor rejection of it proved optimal. This balanced approach to human-machine teaming remains relevant today. Automation continues extending into more domains of human activity. The Mark 18 era offers historical examples of how such partnerships can succeed. Understanding what factors contribute to effectiveness remains valuable. The Mark 18 gyroscopic gun sight deserves remembrance for specific reasons, not because it was revolutionary or single-handedly changed the Pacific War. It deserves remembrance because it exemplifies less dramatic but more important work. Solving practical problems effectively matters more than breakthrough innovations that cannot be implemented. In an era celebrating disruptive technologies and revolutionary breakthroughs, the Mark 18 reminds us of different values. Incremental improvements, when implemented systematically at scale, often prove more valuable. Revolutionary changes that cannot be produced or deployed effectively remain academic exercises. The device succeeded because it was practical, reliable, and adequately effective. These characteristics may not seem glamorous. They define technology that actually makes a difference in the real world. Practical considerations outweigh theoretical elegance when lives depend on performance. The Mark 18 story is ultimately about people solving problems together. Engineers designed the system to meet specific requirements. Workers built it in factories across America. Logistics personnel delivered it to forward airfields. Maintainers kept it operational under harsh conditions. Pilots used it effectively in combat situations. Commanders integrated it into successful operations. Each group contributed essential elements to overall success. Without any single contribution, the entire program would have failed. This collaborative nature of technological success deserves emphasis and recognition. Individual genius matters in technological development. Organized effort across many individuals and organizations matters more. The Mark 18 resulted from thousands of people doing their jobs competently. Each person worked conscientiously within their area of responsibility. That collective effort, more than any individual brilliance, determined the ultimate outcome. Systematic execution across multiple organizations created success. The final assessment of the Mark 18's impact must acknowledge both documented facts and remaining uncertainties. Official records confirm substantial production numbers. The device equipped numerous Corsair and Hellcat squadrons during 1944 and 1945. Favorable evaluations from pilots who used it are well documented. Combat action reports indicate improved accuracy among squadrons equipped with gyroscopic sights. Shorter engagement times appear in multiple sources. Pilot testimony uniformly describes the Mark 18 as a significant improvement. Deflection shooting became more reliable compared to reflector sights. What cannot be precisely quantified from available declassified sources is exact statistical improvement. Kill ratios specifically attributable to the sight versus other factors remain unclear. The 11-to-1 overall Corsair kill ratio represents performance across the entire war. Both sight types contributed to this record. Pilot experience levels varied throughout the conflict. Tactical improvements occurred simultaneously with sight deployment. Declining Japanese opposition quality also affected outcomes. What remains clear is that the Mark 18 represented meaningful advance in fire control technology. It provided practical advantages to pilots who used it operationally. The device exemplified American industrial capacity at its peak. Technological innovation combined with systematic problem-solving approaches. In an era where aerial combat was transitioning from individual skill to technological systems, the Mark 18 marked an important milestone. It pointed toward the automated weapon systems that would define post-war aviation. The device succeeded because it worked reliably under combat conditions. Manufacturing in sufficient quantities was achieved through industrial expertise. Pilots could operate it effectively without extensive specialized training. These practical considerations mattered more than theoretical elegance. Engineering sophistication meant nothing without battlefield effectiveness. The Mark 18 was designed to solve one specific problem. Hitting maneuvering targets during high-speed combat required automated deflection calculation. It solved that problem well enough to remain in service through the Korean War. Years of operational use proved its practical value. For the Corsair pilots who flew with the Mark 18 in 1945, the sight was simply an effective tool. It made a difficult job somewhat easier and more reliable. Danger wasn't eliminated, and survival wasn't guaranteed. But chances improved in combat where margins were thin and outcomes remained uncertain. In broader technological history, the Mark 18 gyroscopic gun sight stands as transitional technology. It bridged the era of instinctive aerial gunnery and the coming age of radar-guided missiles. The device demonstrated that machines could perform calculations faster and more reliably than human minds. This principle would reshape aviation and eventually extend far beyond military applications. The pilots who witnessed this transformation understood they were living through a technological revolution. Aerial warfare would be fundamentally changed by what they were experiencing. The Mark 18 was both an ending and a beginning in technological development. It represented the culmination of mechanical fire control systems. Simultaneously, it served as precursor to electronic systems that would follow. Its legacy lives on in the fire control computers of modern aircraft. Sophisticated descendants of those spinning gyroscopes continue teaching machines to aim. The story of the Mark 18 is the story of technology meeting necessity. Engineering met combat requirements through systematic development. Innovation met implementation through industrial capability. It represents how American industrial capacity and systematic problem-solving transformed aerial warfare in the Pacific. The transformation occurred one spinning gyroscope at a time. Each sight installed in each aircraft contributed to the cumulative effect that changed the nature of air combat forever.